want to connect like this. Okay. Worked.
All right, so as our final speaker for this session, we have Vijay Balasubramanian from University of Pennsylvania, who will tell us about complexity, chaos, and black holes.
Great. It really is great to be back in person. Thank you very much to the organizers for setting up this meeting. It's great so far. Great. So I'm going to tell you about some work that I've been doing lately, which about complexity, chaos, and black holes. I've learned almost everything I know about this subject from the following people: Pavel Kaputa, Javier Magan, and Qingyue Austin Wu, who's a grad student in my group, and also Arjun Kar, Yue, Kathy Lee, and Onkar Parikar. And Kathy is graduating this year, so please keep an eye open for her applications. So I'm giving this talk in the context of the many developments that have happened in our understanding of quantum black holes over the last 10 years. So I would say the emerging picture that we have is a bit like this. You start out with a simple cloud of, let's say, a gas. It collapses. And then there's some process that involves chaos or something like that, which produces a very complicated microstate, supposedly, which has an effective description semi-classically as if it has a horizon. That proceeds to radiate away, so there's some Hawking radiation, which produces maximally entangled pairs between the inside and outside. And our understanding at present is that after the page time, the distant radiation very far away somehow includes a very complicated dual description of the remaining interior. And then after a little while, though we don't still fully understand this, it's all evaporated away, and then the radiation is a unitary transformation of the initial state. Now, as Emil emphasized, much of this progress has been established in 2D gravity, which like you could put gravity in quotes there, because in 2 dimensions there isn't that much gravity, and with a negative cosmological constant. And it would, of course, be great to try to export this to a full-fledged string theory and higher dimensions. But still, this is very important progress because it's taught us, I think, what things are arising just because the system is very complicated in some sense, or what's happening because of gravity per se. So since the 2 key pieces here are that somehow chaos or something like that makes simple things become very complicated, and then the encoding of the interior is very complicated, today my talk is going to focus on 3 things. I'm going to start off by talking about, well, thinking a little bit about what we might want to mean by complexity in these contexts. Then I'm going to talk about the first stage here of how complexity is generated in some kinds of processes. And I would love to talk a lot about how complex is the structure of the Hawking radiation code for the interior, but I suspect I won't have much time to talk about that, so I'll simply summarize results when I get there. So let's start with the first thing. What does complexity mean anyway? So, you know, the ideas about complexity mostly to come to us from computer science. And in computer science, the basic notion is that the complexity of X, a thing, basically counts the number, or the minimal number of simple pieces required to build X. That, of course, immediately has an ambiguity. What do you consider to be the simple building blocks? So there are many ways of thinking about this, and one way in which the computer scientists go about thinking about this is they simply ask questions about scaling laws. You know, they ask about universal rules across many different simple sets of building blocks, and they say that they don't care about the coefficients. In that language, if you were to think about the complexity of time evolution, you know, of e to the minus IHT, quantum time evolution, then following the work of Nielsen, we might say that the complexity of the time evolution in question is the length of a geodesic between the identity and e to the minus IHT in some metric that penalizes complex, perhaps non-local operations. So this particular definition of complexity, coming from computer science, is polynomially related to standard notions of circuit complexity, where you think about time evolution as a quantum computation, and you agree that the number of gates you need to do the computation, then simple building blocks, counts as complexity. And you can certainly make progress even in our field in this setup. So, for example, in this paper, there were a bunch of results. Basically, the way you think about this is you say, well, the length of this geodesic, this e to the minus IHC is getting longer and longer, and the complexity therefore grows linearly in time until it gets cut off because of an obstruction, which could be a geodesic loop or a conjugate point. And you can develop all kinds of physical criteria involving the spectrum and the eigenstates and so on to determine when the complexity growth terminates. And you can even show that at least for integrable and chaotic examples, the conjugate points anyway, terminate complexity growth in polynomial or exponential time, depending upon whether you're integrable or chaotic. So those are all very nice things. On the other hand, there's something that, you might seek a more intuitive notion of complexity in a quantum field theory, quantum theory, that you could sort of handle better in physics. And so here today I want to talk about an alternative notion that's helpful, as we will see in some regards, and is also related to the other one in some regards. So this is trying to quantify the following intuition. If someone told you, here's a simple dynamics, what do you want to mean by that? Well, kind of what you want to mean is that if you have a configuration space and you start the system off, it kind of rolls around, comes back to itself, and doesn't really cover much of the space. And what would you want to mean by saying that some dynamics is complex or chaotic? Well, you might want to mean that it spreads somehow, the system explores the entire space of configuration, spreads all over the place. So if this is the kind of thing you want to say, then you might say that complexity somehow is supposed to be some kind of measure of the spread of the wave function across time in some basis. Immediately, so the basis here is going to be the simple building blocks. And so immediately you'll get a potential ambiguity. You could ask which basis. And the rule in computer science that you should sort of pick a definition that kind of minimizes, a minimizing definition of the complexity would say that you want for any given initial state psi naught to pick the basis that minimizes the spread over time, minimizes the number of building blocks. So you might define from that point of view the complexity of the spread of the wave function as a measure of how much it spreads in the minimizing basis. So how would you go about studying this? So, well, what's time evolution? Well, in quantum mechanics, it's the Schrodinger equation. I d dt of psi is 8 psi. And, well, you can solve that, and here's a power series solution. Psi of t is a sum it to the n over n factorial psi n, where psi n is hn acting on h to the power n acting on psi naught. If we were doing discrete time evolution, we wouldn't worry about Taylor seriesing this. Psi n at the nth time is simply h to the n acting on psi naught. So, in this language, suppose B was an orthonormal basis, then you could write down the distribution, which is the overlap of the wave function psi of t with Bn, and you can find out what the probability is of finding the state in any given basis state n, and that distribution quantifies the spread of psi of t in this basis. So now we've got to pick what basis we want to work with. So, before we do that, before we pick a basis, another thing you might say is that you want to quantify the spread as a number, not as a distribution. So one way of thinking about that is as follows. Here's this distribution that tells you the probability of finding the state in each of the different basis elements. You could compute the entropy of that distribution and exponentiate that. Another thing you could do is you could write down an expression like this. You could say, for example, compute the moments of this distribution and use different moments as a measure of how much it's spread. So the people who study operator growth often study the mean operator size. So for example, that would mean you pick Cn equals n, because n tells you, that measures the average position in the basis that you have. Can I have some water? Excellent, thank you. So we're going to consider a special basis called the Krylov basis, which is a Gram-Schmidt orthogonalization of, psi naught, h acting on psi naught, h squared acting on psi naught. So you basically take all the actions of the Hamiltonian on the initial state and you orthogonalize them. It's possible to prove a theorem that says that for any basis B, the complexity, any of these definitions of complexity, computed relative to the Krylov basis is less than or equal to the complexity computed relative to B for at least some finite duration, and actually forever if the time evolution is discrete. The restriction for at least a finite duration for continuous time evolution arises because we're doing some Taylor series expansions and there are radii of convergence, and we weren't able to push the analysis past some of those radii. The proof in the discrete case is conceptually easy, so let me tell you that. So you start off with the initial state. It evolves a bit with one action of the Hamiltonian. So you add to your basis the sort of orthogonal piece that you need to get to the new state. It evolves again to this state, and you add the new orthogonal piece that you need to get to the new state, and so on. So in this way, you minimize the apparent spread of your wave function in your basis by simply following the orthogonal changes in the state. Repeating this for the continuous case is a little bit messier, but it's the same logic as such. So what's our goal? We would like to find out, since we've agreed that this special basis, the Krylov basis, is the one in which we should measure the spread of the wave function, we would like to start talking about the dynamics by which complexity in this sense of spread is generated over this basis. And I'm going to describe 3 methods that are useful in different circumstances. Here's method 1, which goes back to the work of Lanczos many decades ago, and it goes as follows. So Lanczos gave this prescription, which is a recursive prescription for starting with the initial state and then producing a sequence of states that are orthogonal to that initial state, and that will produce this sort of minimizing Krylov basis. It's essentially a Gram-Schmidt procedure. A better way of thinking about this in some ways is to recognize that once you have gone through this procedure, the action of the Hamiltonian on one of the basis states produces the following thing. It produces the state itself with the coefficient an, and then the next state in the basis and the previous state in the basis with coefficients bn+1 and bn. Some coefficients that you have to determine. In other words, in this special basis, the dynamics of the system gets written out as a kind of chain of this kind, right? The initial state, the next state, etc. Another way of saying this is that this special basis tridiagonalizes the Hamiltonian. That's a useful observation because, very often in physics we're very used to diagonalizing the Hamiltonian to extract the energies, but actually, as it will turn out, for these kinds of applications for studying the dynamics, tridiagonalizing the Hamiltonian is actually a useful thing to do. And if you look in any numerical recipes package like in Python, you will find that actually there are very efficient algorithms for doing this. So for people who want to study these kinds of things numerically, this can be done very effectively. So if you write out the state as psi of t is a bunch of coefficients times the special basis, a way of thinking about this is the time derivative of any of these coefficients takes this kind of chain form. So effectively, what we've done is we've given a universal one-dimensional chain-type dynamics in this basis for any quantum system. It's a very powerful way of thinking about this. So anyhow, once you've solved that, if you set Pn, the probabilities, to be psi nt squared, that's these coefficients squared, then you can apply either of these 2 definitions of complexity, this in one of these moments, or the entropy, or whatever you want, and you'll be able to calculate it. So that's method 1. Here's method 2, involving a thing called survival amplitude, and this is interesting because it builds a relationship with the partition sum and the spectral form factor, which are 2 things that have appeared before in the study of black holes. So again, suppose you write out your state in the Krylov basis. Then we can define the survival amplitude as the amplitude for the state to remain unchanged. So this amplitude, as it turns out, generates moments of the Hamiltonian. So suppose you know the survival amplitude through other means, and we'll talk about what other means you may have in a moment. Then by taking derivatives of it, you can write out moments of the Hamiltonian of this kind. Okay. So how can we use this to solve our problem? Well, remember we described the dynamics of this basis as a chain. Well, if you unwrap the chain, you can draw it like this. This is time 0, time 1, time 2, etc. You start in the initial state, At time 1, you can transition to state 1 or to state 0. At time 2, you can transition to state 2 or 1 or, 0, and so on. And then you can work out that each of these moments of the Hamiltonian in the initial state is a sum of weighted paths through this graph. And by examining that graph, you can see that if you know, let's say, A0 through AK minus 1 and B1 through BK, then it'll turn out that there is a unique path through this lattice contributing to the next moment. So in this way, you can recursively start in the beginning and one by one simply work out every single moment from knowing the survival amplitude, and then work out each of these coefficients in a very efficient manner. Okay. So what do you do to work out the survival amplitude? So let's consider our favorite kind of state, which is the thermofield double, as so. So if I consider the thermofield double state, and let's say evolved with the left Hamiltonian, then psi beta of t, the time-evolved thermofield double state, is, well, the same thermofield double state, but with beta plus 2it. That's because you add a plus 2it here by time evolution. Now remember that the analytically continued partition sum is nothing but the sum on all the energies of e to the minus beta it en, and the spectral form factor is that thing squared. So now consider the survival amplitude. The survival amplitude is the overlap between the initial thermofield double state and the time-evolved state. So just examining all these relations, you can easily see that this is simply the ratio of the analytically continued partition sum, and, well, z beta is the normalization in the first place. Thus, you see that the spectral form factor, which is the square of the survival amplitude, is simply one element of all of these different probabilities that define the complexity of the spread of the wave function. So it's one piece of that. So to summarize, for thermofield double states, you can start with the spectrum, compute the analytically continued partition sum, compute the survival amplitude, compute these Langström coefficients, and there you go. You can calculate how the wave function spreads. You can compute the complexity of the spread of the wave function. Now I'm going to tell you method 3. It's very interesting. So this is a method that is an analytical method that applies to any random matrix model. That, of course, is very important to us because random matrix models are, manifest chaos and have been implicated in various ways in having the same universal dynamics as the processes that form black holes. So consider an n by n random matrix drawn from this measure. This is the normalization here. And then you have e to the minus beta n over 4 trace of a potential. So if you pick beta equals 1, 2, or 4, and v to be quadratic, this would be the orthogonal, unitary, or symplectic ensembles. So here v, the potential, is supposed to be invariant under unitary transformations. We're also going to pick a generic initial state. And since we're picking the matrix generically, just drawing it from the ensemble, we can pick a representative generic initial state like so, as 1, 0, 0, 0, 0 in the basis in which you drew the random matrix. So now I'm going to tell you how to calculate for these random matrices and the generic initial state, calculate all of these coefficients you need to calculate this, the complexity of the spread. So it's well known among physicists that if you look at the spectrum of a random matrix, n by n random matrix, so here are the n eigenvalues, then that the probability distribution is given by the van der Monde determinant times e to the minus beta n over 4 times, basically the potential. And that there's a relationship between the potential and the density of states. These are well-established facts. So it turns out that you can extend some results by Dumitriu and Edelman from 2002, and they derived these results for Gaussian ensembles. And you can extend these to show that if you tri-diagonalize the Hamiltonian, this is the statistics of diagonalizing the Hamiltonian, you can instead tri-diagonalize the Hamiltonian and derive the probability distribution there too. In this case, you get some product over these B coefficients and then some trace over this, some exponential of the potential. So now that you have that in hand, the way in which you can derive everything you want to do is you take the large N limit, because we're often interested in the large N limit, and then evaluate all the integrals for expectation values, fluctuations and so on by saddle point, and you can find this relationship between the average value of these coefficients A and B that you need in these chain dynamics and for your random matrix ensemble and the density of states. So this integral equation, as it turns out, can be solved. And you can similarly compute the correlations in all of these coefficients and work out the statistics of exactly how, for individual realizations of these random matrices, the dynamics will be different from each other. Let me put all of this together. You can get many interesting results about the dynamics of these kinds of systems. So in particular, let's consider the TFD state, the thermal field double state, in the SYK and random matrix models, or generic initial states in random matrix models. So this here is related to the kind of physics that we see in the two-sided black hole, because the SYK model, the thermal field double of the SYK model is related to the two-sided black hole in ADS2. And this is like the one-sided collapse system. So here's what you find. So if you take your definition of complexity, namely as the spread of the wave function, you see an initial quadratic growth, an exponentially long linear ramp, a peak that's of order e to the s, then a slope down, and then a plateau of order e to the s. That's exponential in the entropy. And the peak and the slope, it turns out, depend upon the eigenvalue correlations and the spectral rigidity of the system. So in other words, we are seeing here an example of a way in which a simple cloud of gas, a simple initial state, a generic initial state, via the chaotic dynamics of this kind of system can become a maximally complex internal state. You can also get exact solutions for this kind of thing in integrable models like particles and group manifolds, but you'll find in each individual case, you'll find a different dynamics that's particular to the particular nature of the integrability. It's the chaotic systems that act universally. So what have I said so far? I've said, well, we started with the idea that simple initial states collapse through chaos or something like that into a complicated microstate. And then another place where complexity appears again is possibly in the encoding of the black hole interior in the radiation, because there's this process of entangling the interior with the radiation, and then we're supposed to see some very complicated code. How many minutes do I have left? Okay. So what I'm going to do is, there's no time to describe all the details, so I'm going to give you a summary of how that works out. So suppose you have the radiation in the Hilbert space, the radiation Hilbert space, and the black hole low energy Hilbert space. This is inside the black hole. So the assertion that we make these days is that the radiation contains the inside of the black hole in some sense, holographically. It's dual to the interior of the black hole. It contains an encoding. If so, then it should be the case that some sorts of operators acting on the radiation will affect the interior. So you could ask the question, can we characterize these operators and ask, and we'll do that using the techniques of quantum error correction. So because of the lack of time, I'm just going to go to the result. So here's the way we're going to think. There's the physical Hilbert space, which consists of the radiation plus gravity. And the way you work in quantum error correction is you say, suppose you have some operation which you want to use to perform on the radiation. Then you attach to this an auxiliary environment, and you say that you act with a unitary operator that basically entangles the radiation with this auxiliary environment. You're always free to trace out the auxiliary environment if you don't want it there in order to see how to describe the action on this radiation. What you also do is you create an auxiliary reference space, and you entangle this auxiliary reference space maximally with the physical Hilbert space. And there's a statement that says that the action of this operation does not affect the encoding of the code subspace in the physical Hilbert space, so long as, when you trace out the physical system, the mutual information between the reference and the environment is zero. This is called the decoupling principle. So you can ask to what degree this holds, or what it would take to have an operator that produced such mutual information. So you are acting on the radiation, and you would like it to produce mutual information between the reference and the environment. So you can study this, for example, in one of the standard models that we use now to study these kinds of things. So if you take 2D JT gravity plus matter plus end of the world brain, here's the setting. You have a black hole there's some radiation sitting out here. Here's the end-of-the-world brane, which represents a microstate. And you construct the maximally entangled state of the end-of-the-world brane, so the microstate, with some of the radiation. I'll be done in 2 minutes. So you can do this calculation. So now our problem is to calculate some mutual information. And so this is now going to be a path integral in gravity because you have this setup. You have to do a mutual information calculation between the environment and the reference. The physical space contains gravity. You've got to do a path integral to compute these mutual informations. And you find out when you do the calculation that the mutual information is not zero, namely, you've affected the interior through your operation if wormholes dominate the computation. Namely, in that case, the interior is affected. So you can check what kinds of operations would be dominated by wormholes in this way. So if you consider random errors, for example, if you pick a Haar random unitary acting on the radiation in this case, you find that the wormhole phase dominates when the rank L of the channel greatly exceeds the dimension of the radiation Hilbert space. In fact, is bigger than the black hole entropy, bigger than the exponential of black hole entropy. So what that tells you is that you need exceedingly complex operations to affect the black hole interior. So to conclude, what have I talked about today? So we discussed the picture that we seem to be coming up with as a community is you start up with a simple cloud of gas. Chaos as some other dynamical process produces a complicated microstate, very complicated, and therefore it looks like it has a semi-classical horizon. Then there's Hawking radiation, which produces a system where the radiation encodes the black hole interior in some very complicated way, and then that eventually radiates away. So the three things I tried to discuss to you today was that the word complexity being used in all of these things can have different definitions, and different definitions can have useful uses in different places. The second thing I tried to argue to you was that chaos can efficiently generate complexity. I used a particular definition there of the spreading of the state, for example, and we showed that how it would generate exponential complexity over a period of time. Maximal complexity. And then finally, I told you, although I didn't show you for lack of time, that the Hawking radiation code for the black hole interior is also exponentially complex. We'll stop there.
Question here?
Yeah. Thank you for the nice talk. What happens if in your initial distributions you have divergent moments? Can it happen? And if yes, how can you do the analysis?
You mean in the initial distribution of those PNs that I was talking about?
Yes.
So you don't, because by definition in this kind of a setup, you always start your basis of states always contains your initial state. So the initial system does not ever have divergent moments. So you're starting with the initial state as a vector in the Hilbert space, and then you're asking how it spreads, and you're requiring that you be able to describe every stage of the spread in the same, using the same basis. You're not allowed to change your basis, later on. Otherwise, any state is one vector in the Hilbert space. You could always pick that vector as an element of your basis.
Okay, thank you.
A question with Julian?
Hi, thanks, very nice talk. So since you outline here how this spread complexity has, should work for black holes, do you have any speculations of how you might calculate this, let's say in holography, more directly using gravitational variables?
Yeah. So this is not something we've done, so that's a very good question. And the interesting connection is, especially for thermophile double states, note that I pointed out that the object we're computing is intimately connected to both the partition sum and to the spectral form factor, both of which are related to computations in gravity, where you compute the free energy. We have not thought in greater detail about exactly doing that calculation because we've been trying to do other things on the field theory side, but. So in relation to Shira's talk, for example, one of the questions is there have been these conjectures that, quote, complexity, whatever that should mean in the field theory, is equal to volume or action. Now, the thing is that both volume and action are gauge invariant observables in gravity, so they ought to have a dual in the field theory, right? I mean, there should be something there, but we don't know what, and we also need a definition of complexity. Right. So here, there are some definitions being used that have useful meanings in the field theory. That's the first step. The second step is at least the spread thing that I was talking about is directly related to the free energy. Right. It's related to the partition sum and thus to the free energy, and that has a holographic dual. So there's some connection there that may be interesting to work out.
Okay. On that note, let's thank Vijay again and. There's a short announcement before people head off to lunch.
Okay, thank you very much. A few announcements. The one thing is that we want to lock this room during the lunch break until 1:30, so please leave the room. And then from 1:30 on you can come back, or the speakers can try out the slides and so on. Second announcement, if you find a pair of glasses somewhere, somebody lost it, just bring them to the conference office. So by the way, there's a conference office which you find behind this door. Whenever you lose something or find something, bring it, when you find something, bring it there. When you lose something, ask there whether it has been found. Okay, then I should also announce that Julia Peveri and Melanie Swan should come and find Abiram. What more? Well, I just want to remind you, please wear an FFP2 mask in this hall. That's the rules that we set up to protect us all. So last thing, the lunch will be served in the same place where the coffee break will be. Just use all the doors. You can also leave here, you can also leave there. I guess you find your way to the catering. Okay, see you at 2 o'clock.